What's up everybody, Nick Limon here, helping you get a glimpse at the next generation of video games. Now the state of PC is constantly evolving, with games getting developed for PC first with exclusive features like NVIDIA DLSS, NVIDIA Reflex, ray tracing, path tracing, and so much more. Here with me to discuss the application of these technologies is GeForce evangelist Jakub Freeman.
Thank you for having me.
And VP and Global Art Director at CD Projekt Red, Jakub Knapik.
Hey, thank you.
Presented by NVIDIA. Thank you for joining me. So real quick, Jakub, let's get things started. AI upscaling is the thing that is kind of a common conversation piece nowadays, and some would argue that it is the foundation of modern PC gaming titles, and now the launch of DLSS 4 and NVIDIA's technologies like DLSS transformer model and neural materials are leading the next generation of games. Can you talk a little bit about the evolution of DLSS, how we got to this point, the jump from 3 to 4?
Sure. So with DLSS 3, we introduced, first of all, DLSS stands for Deep Learning Super Sampling. And what it's doing is it's rendering the game at a lower resolution and then using AI to hit your target resolution. So if you're, for example, you have different options to kind of configure it, but just as an example, if you're running DLSS performance mode at 4K resolution, the actual rendering resolution is 1080p, and then it uses AI to hit your 4K target resolution. So basically, it's improving performance. That's what it's doing. So with DLSS 4, we introduced a new model that's called transformer model. And what transformer model does is it takes more data to deliver a better image quality. So you're getting better image quality with DLSS 4 transformer super resolution. In a lot of cases, it can be even better than, like, for example, TAA rendering or upscaling. There's another feature of DLSS that's called frame generation. And what frame generation does is uses AI to generate an entire frame based on data from the game itself. And we introduced that with DLSS 3, and it generated 1 additional frame. For DLSS 4, it's generating 3 additional frames. So you're getting much smoother gameplay, much higher performance. There's also another feature of DLSS that's called ray reconstruction. And what ray reconstruction does is it replaces the denoiser that is typically used in ray trace games. It replaces it with an AI denoiser, which is better image quality. You'll see faster, like when a light changes, when a bounce light changes, you'll see that change happen quicker with ray reconstruction. That also got updated from DLSS 3 to DLSS 4 to also get the transformer model, so better image quality. So basically DLSS 4, better image quality, better performance. That's what you get with DLSS 4.
Yeah, I think the thing that's always kind of baffled me about DLSS 4 in particular is its implementation in something like Cyberpunk Phantom Liberty, where I just remember seeing when the technology was relatively new, it was a great showcase of what DLSS 4 was capable of. And seeing the AI upscaling, like the quality mode looking better than almost native game, I didn't realize that that was possible. Like, my brain could not comprehend it. So it's just wild that we're at a point where we can make something look even better than the real thing to some extent. And you talked a little bit about DLSS getting implemented into other games. For those who haven't, you got to follow Jakub Freeman on socials, because he is so good at showcasing like the latest and greatest in games and saying, by the way, you can inject DLSS 4 into this game using the NVIDIA app. So how do you actually go about doing that? Do they let you know that, hey, you can throw DLSS 4? Or do you just experiment with all this stuff?
Well, some of it is experimentation, of course. But today, DLSS 4 is supported in over 175 games. And that's kind of a mixture between games that have native implementation, like Cyberpunk 2077, for example, has native integration. You don't have to use overrides. You can select transformer directly from the in-game settings. But other games that don't have native integration, you can do so with using DLSS overrides through NVIDIA app, which is the application that you can get when you install the driver that'll give you a bunch of settings. It has a bunch of great features in there, one of them being DLSS overrides.
Yeah, it's something I kind of do in my day-to-day like workflow for playing games. Like I was can I update the game to make it run a little bit better using the NVIDIA app? I love it.
Yeah.
Now, Jakub, how has DLSS 4 brought like new graphical fidelity to your team's workflows for something like Cyberpunk 2077 and Phantom Liberty?
It's a great question, especially for Phantom Liberty. I do need to say that with a big pride is that we were one of the front runners when it comes to path tracing, and we worked with NVIDIA for years. We started with ray tracing in our base game, then we did release our technology preview. That's how we decided to call it, just for kind of like a safety. We're just throwing in like a new rendering mode, the path tracing, and the path tracing was by then. The decision to release path tracing was actually triggered by the fact that DLSS was capable of what it was capable of. And while we released the Phantom Liberty, it was more or less the same timing where DLSS evolved with all the features that Jakub just mentioned. And those are actually critical when you try to resolve the problem of path tracing. Because path tracing, well, apart from all the benefits, maybe we can talk about it later, that it actually brings to the table, it has a lot of technological challenges when it comes to computation. You're pretty much scattering a lot of samples in an environment, and even though you try to help those samples to be located somewhere with important sampling, they're still pretty much scattered around the game. And so, for example, when you try to render an environment with characters in it, and you scatter those points or samples around the space, there's a statistical low chance that, for example, they will land on the face of the character. You're scattering the samples in the environment, right? So like points, like dots. And that's a pretty big problem when you try to actually have a lot of fidelity on the faces. And all the things that Jakub mentioned, like ray reconstruction, for example, all the things that DLSS is doing with this really, really innovative way of denoising, the fact that it's denoising while it's upscaling, it doesn't require a prepass to denoise a classical, I'm simplifying it, but a blaring face to just blur those dots and then upscale the image. The DLSS version 4 is actually upscaling it's denoising while it's upscaling. So it is actually super good at managing the details and respecting the samples that are already cast in the environment to retain the detail on tricky areas like face of the character. So long story short, what I'm trying to say is that actually with all those features, we were able to have, for example, path tracing running in Cyberpunk, Phantom Liberty in 4K with 240 frames per second. When you just process that, the one frame with path tracing in a film, say 10 years ago, required 24 hours to render, one frame. Now we are rendering 240 frames in 4K to play the game. Obviously, we're using a lot of tricks, but when you just flip in your head the math, how much it flipped, this is a breakthrough. And so the DLSS, with this new paradigm of approaching quality problems in general in the image, like in a 2D image, but also sort of with this extra feature of helping to resolve the denoising problems, is really a breakthrough for path tracing and ray tracing to some degree, but path tracing, I would say more when it comes to pure quality on the screen. I can talk for hours about it, but yeah.
No, I love it. And I'm so glad you brought that up, because I think what it does is it allows the just general audience to really enjoy the intended vision of the overall game developers and the creators to say, I want you to experience everything Night City has to offer, and these NVIDIA technologies are helping you experience it the way we intended. And I think ever since the 2.0 launch alongside the Phantom Liberty expansion, I think to this day, like I just got a brand new GPU not too long ago, 5090, and it's always Phantom Liberty that is my benchmark for my new PC. So I want to talk to you a little bit about that, Jakub. When the game launched, what was it, 2 years ago now, 2023, Phantom Liberty?
Probably, yeah.
How did you and the team go about implementing these cutting-edge technologies into a game that was, at the time, now 3 years old? What sort of considerations do you need to take into mind when you kind of retroactively add these new things to a game? I would assume a lot of things may break.
It's a really good question. But again, it's an answer for hours. I'll try to compress it. So, we had an upper hand here, and the fact is that we had a phenomenal relationship with NVIDIA. It's beyond words how close we worked. First on ray tracing back in the day, 2 years before we released the base game, it was sort of research and development project for both NVIDIA and us to really push the ray tracing forward. the fact that we already had that great implementation of ray tracing, and the base idea for Red Engine 4 lighting paradigm in the base game was to be physically accurate, helped a lot. The basic idea for lighting Night City was to create an engine that would behave like a sandbox. When you make a game like ours with a dynamic day-night cycle and dynamic weather system, that means that you have constantly changing environment lighting conditions in a way that is not always, super predictable, meaning that you can have a rainy morning or a sunny morning, plus you have a massive night city. It's a big city to light, right? So the idea we had was that if we create a very predictable lighting engine, one that would respect the physical energy distribution and the physical light sources, we could have a very predictable engine, meaning that you could actually assume that a part of the city that was not necessarily handcrafted, at any time of a day, at any weather state, will present you a predictable, coherent image, right? That was the idea. It's an artistical decision, but it's also a production decision, right? You actually want to have a sandbox environment and predictable outcome. So we spent a lot of time actually fiddling with our Red Engine 4 fundamentals, meaning that the energy conservation was correct. So that helped a lot moving to the path tracing, because that meant that when we implemented path tracing, and back in the time with ray tracing and some offline rendering engines like Arnold, we had a pretty good energy conservation in the engine. Moving on to path tracing, which is the ultimate when it comes to really coherent energy calculations and really accurate, physically correct rendering, the delta wasn't huge. And the fact that we worked almost daily with NVIDIA team, explore new problems and resolve those problems and fix them. And we actually had NVIDIA people talking with us daily on those topics, actually helped a lot. And once we moved from ray tracing to path tracing, a lot of the issues were pretty manageable when it comes to implementation, because it was pretty much always just getting the path tracing to cover all the edge cases of the engine behavior. But yes, there was a lot of back and forth and some cleaning up in the other way around, meaning that we had to fix certain behaviors of the lighting the other way around, meaning for non-path trace solution.
Right.
That's why, for example, there's a very cool feature that comes with path tracing, which is the fact that you can use insane amount of light sources in the game. You can actually cast shadow from thousands of lights on the screen. This is a really cool feature. And so how to use that when you actually create a game that just uses 4 to 10 shadow casting lights in the game. So there was a lot of this okay, this is so cool, we want to use it, but how to retro secure that in a game when you're actually not running path tracing. So what I'm trying to say is that once you pass the implementation phase of path tracing, actually you have even more options. You know what I'm trying to say? Yeah. It was challenging, but it was fun.
Yeah, and I think it's paid very, very well off as, again, just the game that I constantly go back to as my benchmark for new PCs. Now, Jakub, just to touch on games that have been getting added path tracing implementation, obviously Cyberpunk 2077 and Phantom Liberty is a great example of that. But we've also seen it with things like Indiana Jones and the Great Circle. Doom the Dark Ages also got a pretty massive post-launch graphical update. Talk to us a little bit about path tracing in general. First of all, what is it, and kind of talking a little bit about the evolution of the technology.
Sure. So, path tracing in its simplest explanation is the calculation of light rays and how those light rays interact with the environment, how they bounce off objects, how the shadow is casted from a occluding object. That's essentially path tracing. It's not necessarily a new technology, like you were talking about 10 years ago. It's been used in CG for, I don't know, a long,
in
20
VFX
years,
post
more,
houses,
probably more.
In film circles a lot more.
Yes, in film. But it until very recently, it was basically unachievable for real-time graphics. It's just too computationally intensive. And that's, going back to DLSS, that's basically DLSS helped us to deliver path trace visuals at a full 60 FPS more, than 60 FPS.
So you would say right now, the lighting that we're experiencing in the studio is all path trace.
Yes.
Is that correct?
Yes.
So what is the difference between...
And it's kind of, I mean, they can't really see it on screen here, I guess, but if you look at like the green light on that wall there, how it's reflecting off of the wall. And the other thing is, a lot of people think of ray tracing as like reflections.
Correct.
And that's part of it, definitely. But if you think about the environment, basically every surface is reflective. Just some are more reflective than others. And how the light bounces off that wall or reflective object and then hits another object, that's all path tracing.
Now, can you talk a little bit about like the rasterization versus ray tracing leap? Like what is that for people who may not be familiar with that sort of thing?
CDPR maybe could answer that one a bit better.
I could.
Yeah, but I mean, essentially, and I'd love for you to chime in, but previously all the lighting was pre-baked, and there's a pre-baking process, as I understand. But you can talk more to that one.
I would assume that's a lot of man hours right there, right? Like actually having to do all that.
Again, our games are different because, again, we have a dynamic day-night cycle, meaning that sun is constantly moving, constantly when you play the game, and the weather is constantly changing. So actually, we could not bake lighting. But Jakub is right. Most of the games actually relied on the baked lighting. And that was actually, you can automate it. So it's not such a hurdle. The biggest difference is that when you bake the lighting, you cannot change the environment, or you cannot change the lighting in the environment because, you just, it is what it is. That's it. So it's a static scenario. In our game, the environment is dynamic when it comes to lighting, just like my hands right now. So you cannot bake anything. But the difference that I could point out, maybe Jakub, when it comes to rasterizing, ray tracing, and path tracing, is that you can have a global illumination with rasterizing. You can. We have that in our engine. We're using GI probes. It's like scattered probes in the environment. They create like a very simplistic definition of global illumination, and it somewhat works for the diffuse part. But the thing is that when you use rasterizing rendering, actually you're approximating reality. So what it means that you're approximating, you're not really describing the reality correctly, right? So you're simplifying shadows, you're simplifying reflections, you're simplifying diffuse, you're simplifying all those layers. They're just simplified. And just like in Photoshop, you're calculating them separately, putting on top of each other like layers, boom, throw it to the screen. Now, when you introduce ray tracing, and ray tracing is not so bad because ray tracing is just it's a feature that allows you to trace rays, and you can use that for whatever you want. You can ray trace shadows, you can ray trace reflections, or you can actually ray trace, for example, indirect diffuse, which is not a full global illumination, because just like Jakub said, environment has both diffuse and specular, so both diffuse and reflection. So it's pretty complex, but long story short, ray tracing was such a good entry into the more advanced rendering because it allows you to slightly quicker cherry pick which of those layers that I just mentioned in rasterizing mode you actually want to have more accurate. Meaning that I, for example, want to have more accurate reflections. So you can ray trace just reflections, replace that layer with ray trace reflections, and then you have more accurate ray trace reflections in your game or more accurate shadows. But the rest of the layers are still approximated. So what that means in simple terms is that it's like you have 10 people that you're throwing into the room, and every single person is responsible for getting a different part of information about the room, and they don't talk at all. They just are like focused on their part. So one guy is just capturing shadow. One guy is capturing diffuse. The other guy is capturing something else. And that's about it. So the outcome is that, and some of those guys are somewhat lying because they're approximating. So your outcome might look great, but again, going back to what I said just a moment ago about the predictability of the rendering, because some of the layers are approximated, some are more accurate, and those layers do not see each other, that means that you have problems with energy conservation. And that is a very important thing when you really want to have like a really predictable outcome on the screen. And that's what we really needed for Cyberpunk. Now, moving to path tracing. Path tracing is a much more complicated when it comes to calculations, but it's much more simple when it comes to how it is approaching the rendering solution, because it's much more coherent, in-depth way of scattering samples that gather all the information about the lighting, both diffuse and specular, meaning reflections in the world. So you just send one guy just one guy, but this guy knows it all. He needs more time, but he gets really accurate, coherent information about all the lighting. And this lighting is always accurate. And it's energy conservant, energy proper. So because of that, even though you need more time to gather this image, the outcome is always correct. And this predictability part means that you can, for example, in Cyberpunk, get always correct lighting. Doesn't matter how complex environment is, doesn't matter how complex lighting scenario is, you will always get the correct outcome because you're not mixing more accurate layers in ray tracing with less accurate layers with rasterizing. All I'm also trying to say is that it all depends on the game you're making, because maybe you actually want to mix up, maybe you want to break some rules. Then maybe the rasterizing technique is better, or you can actually bake lighting. Maybe it's better, but for games like Cyberpunk, open world, dynamically changing environments with a lot of content on the screen, path tracing is a really revelation.
That was fantastic. I think that was an incredible breakdown. Now, you kind of previously chatted about how you and the rest of the team at CDPR have worked very closely with NVIDIA in terms of developing the technologies needed to make your game worlds possible. Now, Jakub, what does that kind of look like? Do they just say, "Hey, I need path tracing," and you bring that up to the higher ups at NVIDIA and say, "We need to pump out more path tracing"? Like, what does that conversation look like?
Yeah, well, I mean, we have a dedicated team that works with game developers, and a lot of those team members at NVIDIA were game developers before, so they understand, the game development pipeline.
They speak
really
the same
well.
language.
They speak the same language. So, we know what it'll take to get path tracing, for example, into a game, and we work very closely with CDPR and id Software and Bethesda, all of them, on how to use our technologies to best implement their vision for the game. And like in the case of Cyberpunk, it was a dynamic day-night cycle, and like you said, path tracing fits really well for that type of lighting. So.
And you previously talked about how a decade ago this would have been possible because it's just too computationally demanding. Your PC would explode because it's trying so hard. You play one frame at a time.
You'd play at one frame per second, maybe, if you're lucky.
If you're lucky. But thanks to technologies like DLSS4, the transformer model, and the frame generation, you're actually able to enjoy these games at 120 plus frames per second, which is wild to think about. Now, if this reality wasn't possible 10 years ago, let's look ahead a little bit. What is currently not possible that you think is on the horizon for something that we would like to see in game development, if you don't mind?
Well, I think there's always places to go. There's neural texture compression, for example, is something that NVIDIA has talked about, which is a better way to compress textures to not only reduce file sizes, but also increase texture quality. Obviously, texture quality is a big part of how realistic a game looks, so that's certainly one. There's also more advanced ray tracing that can still be done. For example, we recently talked about a new feature called RTX hair, which is a more accurate way to represent how light interacts with hair. So there's certainly a lot more that can be done with lighting, with path tracing, with ray tracing that we still have to explore.
Now, I'm curious about the RTX hair thing. Like, I remember, what was it? I think it was Final Fantasy 15 that had NVIDIA HairWorks involved. Don't mean to throw a curveball at you, but what would be the difference between something like that and RTX hair?
With RTX hair, it's using a new feature on RTX 50 series that is called linear swept spheres, and it's a different way to actually render the hair strands that are it's a more efficient way to render the hair strands, which can interact also better with path trace lighting. And so what it will allow you to do is just have more realistic looking hair when you light it with path tracing. How the light goes through the hair and the different, it looks a lot more realistic with RTX hair.
Jakub, can you talk a little bit about games maybe this year or games that are on the horizon that you think are kind of just a great showcase?
I mean,
of,
there's
like,
so
all
many.
NVIDIA
I mean,
technologies?
yeah, there's so many great examples of path tracing games. Cyberpunk obviously is an excellent one.
Phantom Liberty's nuts, man.
Yeah, I mean, obviously we have Indiana Jones that came out recently. We have F1 25. Also, which is an F1 racing game, which also makes great use of path trace visuals. FBC Firebreak is another one from Remedy, who made the Alan Wake games. Use their engine to deliver it's a co-op multiplayer shooter. So we have a lot of different genres of games that are using this type of lighting system. In the future, we're going to have Resident Evil Requiem, which was announced. That will have path trace visuals as well, and I'm sure there'll be a whole lot more.
Yeah, one thing that stood out to me at this year's Gamescom was Phantom Blade Zero as being just a technical feast for the eyes. One, just because the game is inherently cool, just by nature of the wushu style combat, but just didn't think one of those games that just kind of takes your breath away. You didn't think the technology like this existed to create something that, one, not only looked this good but also ran this well in action. Did you get a chance to check
I played
out
it.
Phantom Blade Zero?
I only played like about 10 or 15 minutes of it, but it's great fun to play. Like you said, looks fantastic, has ray trace visuals, supports all the DLSS tech as well, DLSS 4 transformer, multi-frame generation. So you get really good performance also. I just need to get better at it.
Yeah, it's a tough one.
I need some practice, but I know I'll be good. By the time it comes out, I'll be good.
Well, thank you guys so much for joining me, getting a chance to kind of talk real nitty gritty about all of the exciting technologies that NVIDIA is offering, as well as how it kind of gets practically implemented from a development standpoint. So thank you both for joining me.
Thank you.
PC gaming continues to evolve graphically, with next generation technologies becoming standard in games. This year has already seen a ton of games launch with path tracing, and 2026 is set to see even more elevate their visuals with path tracing and enhanced performance with DLSS 4. Make sure to head over to NVIDIA.com to learn more, and for all things gaming, stay tuned to IGN.